Alright, this is Nathan Reif, and this is my end-of-year calculus video project on continuity and discontinuity. Continuity. Continuity at a point means there's no interruption in the path of a function at that specific point. And continuity on an open interval means the function is continuous at every point in the interval where the endpoints are not considered. Discontinuity, conversely, occurs when there are interruptions in the function, or where any point in the function cannot be defined. There are two types of discontinuities, removable and non-removable. Removable discontinuities is where there's not a point at x equals c, but there is a limit. And non-removable discontinuities is when there is not a limit. Solving for discontinuities algebraically. The first step is to factor the numerator and the denominator, and your goal is to get matching factors in the numerator and denominator. So here we have a function y is equal to x squared minus 4x minus 5 over x plus 1. That factors into this. So you take x plus 1 and set that to 0, and then solve for x, and you get x equals negative 1. And that would be a removable discontinuity, a hole. Vertical asymptotes are versions of non-removable discontinuities. These occur when the denominator equals 0 at any point. So your steps are to factor the numerator and denominator, set the denominator equal to 0, solve for x, and write your answers in the form of x equals. And here's an example. Removable discontinuities, a version of this would be a hole. And these occur when y equals 0 over 0. And there's a shortcut, like in the previous steps. Factor the numerator and denominator. The shortcut is to find the factors that occur in both the numerator and denominator. So you factor them, identify the factors that occur in both, and then solve for them. So you get x equals negative 2 in this example. Okay, so now we have two problems where we have to find the points of continuity and discontinuity of the function. So our first problem is y is equal to x plus 1 over x squared minus 4x plus 3. Factor the denominator. You get x minus 3 times x minus 1 over x plus 1. Set the denominators equal to 0. You get x is equal to 3 and x is equal to 1. So the function would be continuous on all points except x equals 3 and x equals 1. Our next problem is y is equal to the absolute value of x minus 1. This is an easy one. You could solve this one by making a graph, simple graph like this. Remembering that the parent function of the absolute value function looks like this. Then by subtracting 1, you shift it over 1 unit to the right. So you make this. And you can see that there is no break or interruption in this function. So then make it continuous on all x values. Third problem is a piecewise function with multiple questions asking whether the limits and values of specific y values exist. So our first question is, does f of negative 1 exist? We can see here simply that f of negative 1 does exist. It is filled out and it is 0. Next question, does the limit as x approaches 0 from the left exist? If so, what is it? From the left, x approaches 0 right here, and you get negative 1. So yes, it does exist and it's negative 1. Does the limit as x approaches 0 from the positive side exist? If so, what is it? Yes. From the positive side, it exists, and you get 4 right there. Is f continuous at x equals 0? We can see here that at x equals 0, there's a break in the function, so that means it's not continuous. What about from 0, x equals 0 to x equals 4? You can see here from 0 to 4, it looks like continuous, but we have a hole right here, so it would not be continuous. Does f of 1 exist? Yes. Does f of 2 exist? If so, what is it? f of 2 does exist, right here, but there's a hole, so it's not 0, is 4. Is the function continuous on x equals 2? We can see that no, because there's a hole. And for what values of x is the function continuous? We can see from x equals -1 to x equals 0 it's continuous. From x equals 0 to x equals 2. From 0 to 2. From 2 to 4. And then from 3 to 4. All of those would be open intervals.